record. All right, so this is the chapter we're going to be talking about spectrophotometers. Now, spectrum, right? And then photo meaning light, and so electromagnetic radiation, photons, and the meter to mean to measure. And so that pretty much sums up exactly what we're going to do. Okay. Now, whenever you're talking about a spectroscopist, this would be the generalized version of that. What you're going to see is there's actually an entire world of spectrophotometers looking at the various different ways matter interacts with light to help explain what is going on and what we're seeing. Okay. And so this was actually kind of an older methodology to do this. And we still use something very similar to this for what's called Raman. Remember where I was talking about the Raman spectroscopy and the Rayleigh scattering? That's this phenomenon, okay? And so you put in an incident beam, which is the laser here, and it's going to scatter that radiation. That scattered radiation is going to have a slightly different energy coming back out. And that energy is going to be corresponding to the vibrational states of that molecule. And to some degree, the rotational as well. But the rotational is very difficult to get. You would have to have an extremely high resolution instrument to get the rotational energies, which some instruments are, but they're very expensive. I actually worked with somebody that had a Raman instrument that was high enough resolution that you could see the rotational, and you could actually calculate a few of the rotational constants. It's kind of neat. Yeah. And so this is the overall diagram, a simplified diagram for a single beam spectrophotometer. And so what we'll have is we'll have a light source, and then we're going to have a wavelength selector. This is going to be a monochromator. And then you're going to take that energy that comes out of here. You're going to have it's not actually going to be a single wavelength. It's going to be a narrow band of wavelengths. Okay. Some of these could do them down to like fractions of a wavelength. Okay. And so some of them are actually quite good. And what you're going to see here is then you're going to take that wavelength in. You're going to have an incident beam power, right? And then that's going to pass through your sample. And then that incident beam's power is typically going to be reduced by some amount. And that's going to then hit your light detector. Now, on a typical sample here, you're going to see this incident beam reduced in power just by it being a solvent or whatever you have in here. Okay, even the cell will reduce the incident beam by a little bit. Okay, just like the glass does, right? Or the water when you're underwater. Okay, and then some samples will actually have a higher beam that comes out, in which case you have a problem. Okay, that typically indicates you have some sort of luminescence, fluorescence, something like that. Okay. Note that you shouldn't be scattering the light too much here. That will also cause you issues because then it will scatter away and you'll have a really, really large drop here. Okay. Okay. Now, in a single beam photo spectrometer, this is going to be a little bit inconvenient because you actually have to place your sample and reference alternatively into that pathway of the beam. If you take measurements at multiple wavelengths, those references will have to be run at each of those wavelengths, and so you'll have to run the entire thing with the reference, and then you'll have to run the entire thing with the sample. Okay? And so it can take quite a bit of time. It's poorly suited to measuring absorbance as a function of time in like a kinetics experiment because your source intensity and detector are going to will slowly drift apart. So let's say that you took, we're going to use an extreme example, okay? So the person that taught organic chemistry before me at another university, whenever I walked by and they were taking spectra on the infrared spectrometer, they would always have a background that looked like this. And then it would have a bunch of stuff in these places where you'd see CO2 and water. Okay? And sometimes they're positive, sometimes they were negative peaks. Okay. And the reason for that is they took a background on like the first day of the week, and then they just used the same background for all their spectra. Now, because the instrument changes over time, right? The instrument's going to warm up. It's going to, the light source is going to warm up, so it'll slowly get stronger. Your parts are going to settle around depending on the temperature in the lab. And then you're going to also have different amounts of CO2 and water in the atmosphere, right? And so what was happening here is those effects, these were the CO2 and water changing in the lab. And then this right here is actually your instrument changing. The background should have been straight right here, like this, not bowed like that. Okay. And so, that's an extreme example of really misusing an instrument. But even a small difference of like 5 minutes, 10 minutes, is going to cause some changes, right? So when you're trying to do a kinetics experiments, this is not how you want to do it. It's very difficult to do a kinetics experiment this way. Okay. On the other hand, you can use what's called a double beam spectrometer. And so again, you have your light source, you have your monochromator right here. And so it's the exact same setup up to here. And then what you're going to do is you're going to have what's called a beam chopper. Okay. Essentially, it's a mirror that rotates. Right. And so what happens is part of the time the beam just goes straight through, and that's your sample cuvette. Part of the time it's going to go off, hit a mirror, and go through the reference cuvette. And so these are then going to alternate on this next part. These beam choppers are typically going to be matched. So it blocks one, only lets the other through. That's timed in correspondence with this. Okay. And so what you'll do is you'll rapidly take reference sample, right? And you're essentially going to do that for each point along your wavelength you're scanning through. Okay? So you'll scan your different wavelengths through, and you'll do a reference sample for each one. Okay? Now, typically speaking, you don't just do that once for each wavelength. You'll do that like 30 times for each wavelength or something like that. Okay? Maybe 16 times if you don't have, if you need to respond really fast. Okay? If you need to get really fast, you might do it only one time. Okay. And so what's then going to happen is you're going to be taking back and forth very rapidly. Your detector is going to be detecting your reference, sample, reference, and then sample, right? And then the electronics are going to do some math where it takes that sample minus the reference, and it's going to give you that in a display of some sort. Okay. Now, for reference, the scanning monochromator right here, this actually typically works through Fourier transform these days. And so this electronics can also be using a Fourier transform. Okay. Typically you get a FID, free induction decay, from this. Did you ever talk about FID, free induction decay at all before? Okay. Typically, it shows up in like chemistry, but actually, I'm kind of surprised Nilling didn't go over that with you guys because he seems like a spectroscopy guy. Okay, that's okay. So what you actually get is when you're looking at these monochromators for modern instruments that are Fourier instruments. Okay, it's called a Fourier transform FT instrument. Like this is an FTIR we got. What you actually have is you have a red laser, and this red laser is a very, very precise, accurate wavelength. Okay, and then you have a source for the IR. It's called a glow coil, and this is going to be the infrared source. So this is providing that infrared radiation. That might be 3,000. Wait, no. Okay. And then we're looking at like hydrogen stretches. Okay, so what you do then is these adjust with each other against another mirror set. Okay? And so what you do is you selectively adjust these that red laser is going to be acting as a essentially a little measuring stick for that. Okay. So what you'll get is you'll get the strongest wavelength coming out, being this like 3,000 wave numbers, based on the number of increments of the wavelength of the red laser. Is that making sense? Okay. Now, what you do is, I'm not going to go into mathematically because this is very complicated math. A pretty simple spectra can take like 3 to 6 months to do the math for this for a graduate student working all day, every day during that time. So it used to be like that was an entire project just Fourier transform. Computers now make that really fast. It happens almost instantly. So what you'll actually get from this is what's called a Fourier transform. And so what you'll get, this is an FID, okay? Free induction decay that we're going to look at. And you take this and you transform it using a Fourier transform. And this is what you're actually going to see in terms of the, like, it's this intensity for this frequency. And this FID typically looks something like, and it is utterly unrecognizable to a human being. Nobody would actually, you can kind of get a sense of like, oh, I have more intensity here. But that's kind of it. It's almost useless for a human to look at. For reference, it looks something like this for the FID. You're looking at this. And so it's kind of like useless without the Fourier transform. But the Fourier transform happens really fast. And so that would be part of your electronics there. Okay. It is, again, this is a kind of simplified schematic of these. Now, again, you're going to have your sample going through the sample here. And so that's going to be your P, right? And then your P0 is the one going through the reference. And so you'll take that difference every time. Now that circuitry is going to automatically take the P and P0. It's going to put you in your formula. Hey, how you doing? And that's going to give you your transmittance or absorbance if you do the log. Now, this right here is what an Agilent Carry 300 UV Vis double beam spectrometer looks like inside. As you can see, it gets a little bit more complicated once you get into an actual instrument. But notice it is still the same setup. Okay. So right here's your light source. And this is, in this case, it's going to be an ultraviolet lamp. Ultraviolet visible lamp right here. Right here's the visible lamp. There's the ultraviolet. And so what you have then is a set of mirrors that you can move this through. One of the reasons you always take it through a set of mirrors is much like a camera, you can get incident light that reflects off the surroundings. So if you were just to expose directly from here to your sample, you'd have light going in the different directions, right? You'd have light going here, 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 here. The ones that are just a little bit off are going to give you slightly different signals and scattering, and you're going to have a lot of problems with that, right? And so what we want to do is selectively get a very narrow beam that we're using. And so then what's going to happen is we have our monochromator. This is where we're going to select for a specific frequency or wavelength. This is then your energy slit right here. This narrows that beam down very much further. And then you take it through a mirror, and then you go on to a grating. Do you guys know what gratings are? You guys ever seen the backside of a CD? Okay. It's like shiny and it separates the lights. It's actually a grating. So that one's not meant to, well, it is technically meant to separate light, but it's not meant to do it for your eyes. It's meant to do it for a CD player, right? But what they can do is, depending on the distance between these physical objects, the grating, literally like a grate, okay? That grating is going to cause different separations of the light. And so if you use this grating and you just move it slightly, you're going to basically get the same effect you would from like a prism, okay? For this light coming back off. Is that making some more sense? Okay. They use that a lot in the. Have you ever seen reflective tape? They put on stuff. That's actually how that's oftentimes done. That's just plastic that they've cut a grating that reflects different frequencies of light, often a kind of rainbow pattern. So you can actually get very cheap grading now, but for high precision instruments, they have to be much more accurately done. Funny enough, MIT used to get the majority of its science department money at one point by selling gratings. So they made gratings for instruments and then sold those. And they could make very, very accurate gratings. So, anyways, this goes off another mirror. This is then the exit slit so that you eliminate anything that reflected, just a little bit off. And so you get a very narrow, very specific wavelength. Again, you bounce it on another mirror to get it into the correct orientation. This is then going to go to the chopper. This chopper is essentially a mirror that's rotating. And so part of it is going to come off and bounce back to where you want over here to this mirror. The other part is going to either get absorbed or not going to go onto your sample. Okay. So this part right here is the next portion. So what we have here is we have the chopper that's right here. And so what we're going to get here is we're going to get the chopper coming along. See how it bounces into here? And this angle here at this mirror will reflect it up to here. But if we had another mirror that blocks it here, this reflection is going to bring it back onto the mirror and going to reflect it to this side, right? Can you see that? And so that's actually what's happening here. So if this mirror position is in between the beams, right here, this is going to reflect it back into your sample position. If this mirror position is not between the beams, then it's going to go on to the reference. Okay. And these are just rotating very rapidly. Okay. And so this part right here, we have it going through the sample versus the reference alternatively. They come back over, and these mirrors here, again, are going to be your chopper. So this chopper is going to be synced with that chopper so that you get your signal going on from this one, going on to your detector, and then the signal going on from this one alternatively. Okay? And it'll go back and forth on which one it's detecting. Okay, so this right here is your detector portion. This is called a photomultiplier tube. It's essentially to take a relatively small signal and then we boost it up. This does cause some degree of error in your system, but it's a lot less error than just using more and more and more light source because these slits are narrowing down our amount of light source. By the way, these are things that you can usually change in instruments. So, for example, you can usually change the slits and how much your what's called an aperture is open. And so if you close the aperture more, you'll get a much more narrow frequency that you're choosing. If you open the aperture, you're going to get more light. But your frequency is going to have more error in it, right? On the other hand, what you can do here is you can actually increase what's called the gain. Have you guys ever heard of gain before? Okay. So have you ever noticed that if you have a speaker system, like a headphone system, and you control it on your phone versus the speaker, like if you turn down your phone, but then turn up the speaker instead, you get a lot of pops and sort of sounds. Okay, that's high gain. So it's amplifying the signal it's getting. And on the other hand, if you turn your phone up and then turn the speaker down, right, you get a lot less pops. And that's because it gives a stronger signal and doesn't have to use as much gain to amplify that. Okay? Okay, does anybody have any questions? Okay. This is what that looks like. So when you use the instrument, that's what you see. And so for most people that don't go through some course like this is really just a black box, is what that's called. It's a box. They have no idea what's in it, and they don't care, and it kind of works by magic. Yeah. And now, I mean, it's true, right? Like, if you were to go into the biochemistry class and be like, how does this work? I mean, biochemistry uses this instrument fairly often. Actually, maybe this exact instrument, I've never actually checked which version they have. But considering that they like buying from Fisher a lot around here, it probably is an Agilent something. Yeah. It probably looks, it does look almost exactly like that, so I'd have to check. You might actually, you'll have to check and tell me which one it is. I forget. If it's the Carry 300, congratulations, you know exactly the insides. It sounds about right. It's the Carry 3 or 400, I think. Yeah. So this has evolved over the years, of course. Again, though, it uses the same principles, but it shrinks the number of pathways so you can get smaller instruments. It gives better sources that are more selective for frequencies. Yeah. So there's all sorts of innovations that happen in different instruments. There's slightly differences, but the overall, what I've told you, is going to more or less stay the same. Okay. There's actually some alternate chopper mechanisms you can do, which are kind of cool. And different ways of splitting. Instead of using a chopper, you can actually use a beam splitter. But for that first one. But again, choppers usually work just as well or better. So let's talk about some lamps and lasers. These are two of the primary sources of light you're going to see. So the ideal characteristics for a continuum light source is going to be a broad emission over all wavelengths that's intense and it's stable intensity over time. That doesn't change dramatically as you use it. Okay. Now, having said that, these are your ideals. What does ideal actually mean? The conditions we want, but is that what we have? No. We're never ideal, right? And so in reality, you will always have some of these not being as true as you would like. Okay. For example, the infrared instrument we have here, it is not actually stable intensity over time. The longer you have it on, the more intense it will be. Now, it's not a huge difference. So if you're using it like all day, you probably won't see a difference. But if you were to look at like a week from now, you'll probably see a difference. Okay. In terms of the intensity. Yeah. The broad emission over all wavelengths is also not completely true for any instrument. Okay. So you have places where you have better emission and worse emission. So you have greater and lesser. All right, so when an object is heated, it emits radiation. Yeah, you're all very aware of that, I'm sure. Even at room temperature, objects will emit infrared radiation. And so this is how, like, an infrared, you guys all know infrared vision. You've seen that in, like, a movie or something, at least. Yeah. Yeah. Predator. You know, they tested that mud thing, a group did, using the best infrared vision that's on the market. And they found it actually did work. Which is, yeah, I didn't expect that. Yeah. So black body radiation. This is the radiation emitted by what's called a black body, and so the energy and spectral distribution of emission is going to depend only on temperature of the black body. Okay. This is a little bit different than, like, most objects are not perfect black bodies, but this gives a pretty good approximation for most objects in isolated environments. Excitance, M, is going to be the power per unit area radiating from the surface of an object. And so this is the power right here per unit area radiating. This right here, sigma, is the Stefan Boltzmann constant. You'll notice Boltzmann, the population guy from physical chemistry. Yeah, same guy, as you can imagine, right? Because this is actually a population distribution as well. So this right here is what that comes down to and looks like. What you'll notice is that as you get higher and higher energy, right, what you get is two things. You get higher intensity and you get higher frequency, right? Higher energy light coming off. Okay. And so this is why, for example, you have an object at room temperature, it gives off infrared radiation, right? And not a huge amount. And you get up into like start heating it a little bit, it gives off more infrared radiation, right? So like your body temperature gives off more infrared radiation. And then you start getting up into like, oh, now I'm in an oven, right? And I'm heating that steel to a very high temperature, and all of a sudden it's visible radiation, right? And if you get high enough, you can start actually giving off ultraviolet radiation. Okay? This is why the sun, for example, gives off ultraviolet radiation, because it's very, very, very hot, right? Okay, so the maximum blackbody emission for an object at 300K is going to occur at your infrared wavelengths. And so if you heat a glow coil, a little coil of metal, to 300K, you're going to get, it's not perfectly distributed here, but you'll get a very nice coverage of the infrared radiation. Okay. Notice that 300K, is that particularly hot? No, it's like 30 degrees Celsius, right? So it's not very hot, is it? Not even like, you wouldn't even consider that warm. It's above room temperature. Yeah. The surface of the sun is actually going to behave like a black body. Its temperature is going to be nearly 5,800 Kelvin. And so what you see is it mostly exhibits visible light, but it has a fairly large quantity of ultraviolet that it releases as well. And then it curtails downwards here. Notice, though, that even the downward slope here is always higher than the previous temperatures. Okay. So Earth's surface is being warmed by the sun. It's going to emit infrared radiation. This is going to be partially absorbed by what we call greenhouse gases in the atmosphere. This partially radiates those down back to Earth. And so that's actually the greenhouse effect, is greenhouse gases re-radiating out what is primarily infrared radiation. Because what sort of temperatures do we see on Earth? About 300K, right? We don't see 3000K, do we? Yeah. And so if we were 3000K, then the majority of our radiation, like 5000, 3000K, would be in the visible, right? That'd be the majority of the energy being re-radiated back out. Okay? But instead, it's around 300K, so infrared is the majority. Notice if you're down in 100K, if we were much colder, we would actually have a lot of microwave radiation coming back out. And so our greenhouse gases would actually be the ones that absorb in the microwave better. And if we were a higher temperature, we'd actually shift what is the more effective greenhouse gases. So CO2 wouldn't be as effective anymore if we shifted up to a higher temperature by a lot. So it's, interesting things to think about. This actually explains a lot of the greenhouse effect and how that works, okay? So this right here is an overall graph of these inputs and outputs that we're looking at for the greenhouse effect. And so this right here is the energy coming in from the sun and the visible radiation. What you'll see is that part of this energy just gets refracted back off from the atmosphere, because if you ever look at the Earth from external, there's a fair amount. Have you guys seen space shots of the Earth? Yeah, right? And you see like this corona of light almost, right? That corona of light is stuff being refracted and scattered off. It's not stuff that hit the Earth, right? It's stuff that got scattered. And then what we have here About 23% of it is going to be absorbed by the atmosphere. This will include things like the ozone layer, by the way. That's a part of that. But also things like, you notice the atmosphere is absorbing a lot of light today. Yeah, it's a bit more than 23% today, right? But this is sort of average numbers. Okay, so that's 23% of the remaining energy. This temperature is going to be about 254 Kelvin up on that upper atmosphere level. And so notice it's quite a bit lower temperature up there. Though keep in mind that in terms of temperature, what happens is temperature drops as we go up, and then it actually goes up again because you start absorbing this light, right? The high energy light. And so you actually get spots in the atmosphere which are higher temperatures. Okay. And so don't think it just gets colder as you go up, as you can kind of see from here, right? It's not as cold as you would have thought. Okay. And so your incoming energy that comes into the Earth is going to be about 160 watts per meter squared of energy. And this is going to be absorbed by the Earth. This is what's warming and heating the Earth. Most of that energy doesn't actually get refracted back off, but some of it does. Okay? And that's what you're seeing the Earth with, aren't you? Like, oh, the blue ocean, so pretty. That's the energy that's coming back off and being reflected by the Earth, right? But a fair amount of the Earth is darker colors, right? And so we get less of it coming back off. They heat up. Okay. And so that's what's going to help heat the Earth to 287 Kelvin. It's not the only thing that's heating the Earth. There's actually radioactive breakdown inside of the Earth that gets recycled quite a bit, and that's the geothermal energy. Okay. But that's one of the primary things heating the Earth. Without that, it would definitely not be warm enough for life. Not even close, right? And so what's going to happen here is you're going to have that, well, it's a black body, right? Essentially. Okay. And so it being somewhere near 300 Kelvin, we're going to re-radiate back out, mostly infrared radiation, aren't we? Okay. And so we'll re-radiate out infrared radiation. This is going to be 398 watts per meter squared. What's going to happen is that is going to come out. Now, as it comes out, you can think of it as layers of materials absorbing, right? Just like a spectrometer. Okay. So we have our source, right? And we're going to have these layers of CO2 and methane that are the greenhouse gases. I know that everybody's put them like clouds because it's a nice way to make the label stand out, but they are not clouds. Clouds would cause refraction, right? Not absorption, okay? Which means they're not the greenhouse gases you're looking at. The most prevalent one that absorbs the most and is the largest effect for greenhouse gases is actually water. Okay, CO2 though being the famous one because that's the one we can actually have some control over. We can't really do anything about the water without just like killing off all life on the planet. Yeah. And so what happens here is the greenhouse gases absorb certain frequencies of those infrared radiations, depending on what their infrared spectra would be, right? And when they absorb that radiation, some of it gets converted to heat and some of it gets re-radiated back out. Now, when something re-radiates back out, it does not. Which direction does a molecule face? Let's say this is the Earth. Which direction does a molecule face? Like that? Does it face this direction? Yeah, it constantly rotates, right? Molecules don't face a direction, do they? And so when a molecule is rotating and absorbs energy, the direction it re-radiates back out is random. It's completely random. And so what you get is essentially half of that energy that gets absorbed by greenhouse gases gets thrown back down towards the Earth, but essentially half of it gets thrown back out. And then, parts of it get thrown the two directions too, which don't really change anything. Because, half of it's going this way half of it's going this way, and then there is a portion that's just sideways. So again, that's not really changing that much here. And so what happens is, yes, it can get reabsorbed by the greenhouse gases as it travels back down, but it can also do that when it travels up. Okay. And then it can change again. Okay. But overall, what we're doing is we're recycling a portion of that energy, and that's what we're looking at right here. This is the infrared radiation from the atmosphere to the Earth coming back in. Okay. And so that's coming back in here. Right. Anybody have any questions? No? Okay. Okay. Did that make some sense? And so we end up losing a fair amount of that energy back out of the atmosphere. Is greenhouse effect and our greenhouse gases, are they negative? Are they a bad thing? They're just a thing, right? Okay. It's like saying water, is it a good or bad thing? Well, when you need it in a desert and you need to drink it, it's a great thing, right? When it comes down in tons and it floods you out, it's a bad thing. Okay. It's same thing here. They just are. The major greenhouse gases is water is the biggest one by far and away. CO2 is the next one. And then far lesser extents, we have ozone, which is a greenhouse gas, but is not really something that we can do that much to fix. Except for cities. Ozone does get created by photochemical smog. So we can reduce that. But CFCs are also a greenhouse gas. Methane is a major greenhouse gas. Interestingly enough, everybody thought that the global pandemic and the shutdown from it was going to reduce global warming. It did not. It actually increased global warming. So we actually made up for most of the global warming effect by an increase in the methane release. Kind of an interesting factoid. Yeah, that was quite a sound. Was they're fixing the floors? Yeah, kind of did sound like it, didn't it? Yeah. And this is referred to as NOx, by the way, nitrous oxides, which are again something pretty common from photochemical smog, that sort of thing. Okay. Anybody have any questions? All right. Now, in terms of a greenhouse effect, you can actually see the two examples of the two extremes of greenhouse effect on both sides of the planet Earth. Everybody's aware we're the what number planet are we? Yeah, third rock from the sun, right? You've heard that title. So there is a planet that is closer than us to the sun. There's a planet that's further from us. Do you guys know those planets? Venus and Mars, you got it. And so Venus, very famously, is very, very hot, right? Now, in terms of just distance from the sun, we should only be a few degrees different, okay? Venus is like melt lead hot on the surface of Venus, okay? And the reason for that is it has a tremendous amount more greenhouse gases than we do, okay? We're talking 10,000 times. Now, it is not all CO2. They have 10,000 times CO2, but they also have sulfuric acid in the atmosphere. And so we've only ever been able to land a probe on Venus for 11 minutes, and then it got destroyed. And that was actually the Soviets that did that one. So Mars, on the other hand, is very, very, very cold. Okay. And that's because Mars has much, much less greenhouse gases. Okay. And so they have very little greenhouse effect, and so they're far colder. They don't maintain that extra energy. Okay. And so, again, greenhouse gases are not necessarily a good or bad thing either way. Okay. Now, they've started labeling it, which is a much better label, climate change. That is a far better label than global warming. I'm glad they finally moved to a label that actually makes some damn sense. Because, climate change is just a better overall label. However, what you'll see is that the additional CO2 that's been put in the atmosphere is approximately 2 watts per meter squared, its area, of radiative heating. That gives you about 0.9 degrees Celsius on average. Yeah. So it's about 1 degree-ish on average. This is not something that's going to be a huge change, and all of a sudden we get. Have you guys seen those graphs? They're called hockey stick graphs. Every time you see a global warming report, you see them, and so they always look like. Just turn on here. They always look like this. Yeah, that's what's called a hockey stick graph because it looks like a hockey stick, right? Okay. Most of those graphs are incredibly misleading. They are intentionally made to exacerbate this effect and make it look exponential here. In fact, the effect is going to be more like that, a sigmoidal. Okay? And so we'll get a rapid increase for a little bit and then tailing off, and it's not going to be a hockey stick at all. But what will happen is, this 0.9 degrees Celsius difference, it doesn't sound like a lot, but what it does mean is that, for example, we've had 3 times less cold days in a given year. So we get a lot less cold days is what we actually see. Okay. And that does throw off that plus the little bit of ocean rays that we're going to get does throw off ecosystems a bit. And so we're going to have a mass extinction event. We already are having a mass extinction event because we already actually, the one that kills me is nobody seems to ever not enough people are talking about it is the overfishing of the oceans. That one is brutal. We've killed off 90 something % of fish in the ocean. Jesus. But anyways. Yeah. The sad part is, we would actually get better yields if we put in fish preserveries. But we just can't get the damn countries to do it. Yeah. Even in the United States, we can't get it done because we have too many treaties. And there's too many groups that can fish for various reasons. Yeah, crazy. So the quartz tungsten halogen lamp, this is a very good source for continuous visible and near infrared radiation. The tungsten filament is heated to approximately 3,200 Kelvin, produces useful radiation from 320 to 2,500 nanometers. And so it gives a pretty nice, consistent frequency here. Now, the infrared radiation in the range from 4,000 to 200 wave number is actually obtained typically from a silicon carbide glow bar. That's what that's called. Okay. That's the majority of instruments nowadays. Okay. And this is right here is the deuterium lamp. You can use this for the lower wavelengths right here. That would be the below 400 wavelengths. Notice that there isn't really a single light source, though, that you can use and covers every region, right? Okay. By the way, this is why the huge difference in price between a UV vis instrument and just a visible light instrument, if you're ever wondering. Because visible light instruments can just use LEDs to cover the different parts of the spectrum, whereas a UV vis instrument needs more advanced lamps. More pricey lamps, I should say. So arc sources, this will provide continuum emission, predominantly in the UV radiation form. Electrical charge through a suitable ionized gas This is the deuterium arc lamp. That's that deuterium lamp we were talking about right there. And so you'll have a controlled electric discharge. It'll cause your D2 to dissociate. This is going to emit radiation from 110 to 400 nanometers. And this is what that looks like. Okay. Xenon arc lamps, on the other hand, the electrical discharge in xenon gas. It's going to provide this is quite an intense continuum emission, by the way, from 175 to 1000 nanometers. Have you ever heard of like xenon signs? Yeah, this is similar to that. Okay. You'll notice that part of this is actually invisible light. So you can actually use this for a visible light source too. It's just expensive. So you typically you'll have very sharp emission lines in the 800 to 1000 nanometer range, which is more in the visible section. So you can see some of that. It's pulsed to lower power consumption, and that also helps to extend the lamp lifetime. So you pulse it to make pulses of light. Okay, so let's talk about line sources. The electric discharge arc lamps filled with mercury vapor can provide very intense, narrow atomic emissions at just a few UV invisible light wavelengths. You can use a monochromatic emission from this by using optical filters, bless you, for the absorbance measurements. Fluorescence lamps are going to be a type of mercury electric discharge lamp. So typically what you have here is some sort of glass tube. It's filled with mercury vapor. The inner walls will be coated with a blend of red and green phosphors. This is actually your luminescence substance that you're going to energize to cause luminescence. And so the mercury vapor is then going to be excited by electrical current. It's going to emit UV and visible lines. The red phosphor, which is EU3+, doped with Y2O3. The green phosphor is TB3+, doped with that mess right there. This is going to be the mercury emission itself will appear blue. The UV radiation will be absorbed by the phosphors. And so the red one is going to emit red light. The blue one or green one is going to emit the green light. And so that gives you red, blue, green emissions. Together, these would give you a white color to your eyes. So let's talk about lasers. This can provide isolated lines of single wavelength for just a tremendous number of applications, actually. Yeah, there's a lot of things that have lasers in them now, right? Now, one of the things to keep in mind is whenever you use lasers, make sure that you actually read the safety guidelines for them. Don't just like smack a lab grade laser into something and shoot it off. Some of the lab grade lasers, first off, most lab grade lasers can cause blindness. So if you don't have the proper glasses for them, they're very likely are going to blind you the first time you accidentally like put something reflective in there. Okay? Or something that causes scattering. On top of that, many lab grade lasers for things like Raman instruments are going to be powerful enough that they can actually like burn small holes in doors and stuff. Okay, they can actually burn stuff. And so if they hit your anything sensitive, you're going to be really regretting it. Okay? I know one person that had goggles on, luckily, that accidentally put something that scattered as a biological sample into our laser where we had at UMKC, and he had a tan over his entire body because of it, like a sunburn. All those exposed surfaces. Yeah. And there was a small burn patch on the door. Somebody had turned it on without the mirrors in place when they were working on it. Yep. So some of the properties of laser light is it's monochromatic. It's going to just have one wavelength. It's extremely bright. This is due to the intensity. It's very high power at that one wavelength. It's collimated. Collimated means it's in a column, right? So it is parallel rays. Okay. the rays are highly coherent. That's one of the reasons it's so intense. It's polarized, so the electric field is going to oscillate only in one plane. So instead of it having where it has the different planes of oscillation, okay, you're just going to have it only in one plane. And so, for example, you can greatly reduce the intensity almost to zero if you get the right polarized lens in place, because it's just going to be in one plane. Okay, so like you could take a pair of polarized lens sunglasses and put them in, and if you rotate it correctly, it's going to block almost all the light. Like 9.999 something percent. Now, it's also coherent. That means that all the waves are in one phase, and you don't have waves that are causing destructive and constructive interference, like your typical like flashlight or light source, right? Most light sources are not coherent. Laser is actually an acronym for light amplified by stimulated emission of radiation. This was actually come up by the graduate student that was on the project who made money off of this acronym. And so he retired early. Charles Towns is the person that actually developed the laser, and he was the professor. I think my advisor was the only person that ever liked that guy. Everybody else hated him because he'd ask really, really tough questions anytime you talked in front of him, and like try to break people. And he was very smart, so he was very successful at breaking people. And so his own graduate student that named the laser did not share any of those precedes or credit with him for naming. Yeah. Laser's an acronym. Well, it's right there. Yeah. So these are the operational principles of a laser. There is many types of lasers now that have been developed off of these principles. So this is the energy level diagram here that we'll need to discuss this. So broadband radiation from a powerful lamp or an electric discharge is going to be directed into a medium of some sort. And this is actually where the naming of those lasers comes from. You'll see it's like a helium neon laser or various different, usually a noble gas paired with something, but it doesn't have to be. And those are actually what you're directing that radiation into. Okay. And so that's what's called the pump. Okay. And so you direct that radiation into that substance. Those molecules that were in the ground state, the E0, are going to be pumped by that radiation source to an excited state. This is referred to as E3. Okay, everybody got that okay? Okay, so you excite them with the energy source. Typically a lamp, though, can be an electric discharge as well. Okay, depends on the type of laser you're looking at. So molecules in E3 are rapidly going to relax to an E2 state. This E2 state is just a state that has a long lifetime. Okay? And so because it has a long lifetime, it's going to gather up a population of it. So you pump a bunch of molecules to E3, they relax down into this E2 state. That E2 state has a much longer lifetime than the E3 state. And so it gathers up that population there. Okay? Now, this right here, this relaxation, oftentimes this is going to be heat energy that's being given off. And so lasers almost always need some sort of cooling source. And you've probably experienced this if you ever used a laser pointer for a long time. It starts getting pretty hot, doesn't it? And so that's actually that energy coming off right here. Okay. And so what's then going to happen is that E2 state is then going to decay to the E1 state. That right there is a population inversion. It's going to radiate that energy out, and that's typically going to be where you have that the lasing effect, the light that's coming off. Okay. This right here is then going to be a further relaxation down from the E1 to the E0 state. That's going to happen fairly rapidly usually. Okay. The exact energy states of these is actually what gives you your color or your electromagnetic frequency of that laser, right? So whatever energy gap this is, that's what gives you that frequency, that wavelength. Okay. And that's why you do different compounds in there and you dope them with different substances to get different frequencies. Okay, so this is how the laser actually looks inside of it. And so this is the one mirror right here. This is the 0% transmittance mirror. And this is going to have the energy coming in to your lasing medium. That's the whatever you're targeting, the helium, whatever. And this is going to give off light. And so what's going to happen is it's going to bounce back and forth here. Okay? And it's going to build up. And what you do is you have zero transmittance layer on one side that doesn't let anything through. And then a 1% mirror over here. And that's going to let light through. Okay? And so what you're actually seeing in a laser is this 1% side letting the light through. That's what's letting it through. That's the front end of that laser. Okay? This is why this is coherent, by the way, is because it bounces it back and forth through that lasing medium. And so it gets a coherent beam there. Now, your E0, rapidly reacting down to E0, this is going to keep your population E2 greater than the population of E1, which is the population inversion. And so you're always going to have, as long as you keep providing this pump energy here, a population of E2 that's greater than population of E1. Okay, so let's talk about stimulated emission. So a photon with an energy that exactly spans two states. This can be absorbed to raise a molecule to an excited state. And you're all kind of familiar with this at this point, I think. Alternatively, the same photon can stimulate the excited molecule to emit a photon and return to a lower state. This phenomenon is going to be called stimulated emission. And so what we have here is we would have a already excited state. When we pass that energy through, it's going to cause this excited state to relax instead. And so then we're going to get a coherent photon that adds to it. This is actually one of the key principles of your laser, right? Is we're passing that light back through. And so any excited state ones are going to relax and emit another photon that matches. Okay? And so this just builds up, builds up, builds up. Is that making some sense? Okay. Now, one of the important factors here is that, some of the important factors, I should say, is that the pumped energy directed through the side of the lasing medium actually is what's going to create that population inversion here. One end of the laser cavity is going to be a mirror that reflects all light. The other has to be a partially transparent mirror. It doesn't necessarily have to be exactly 1%, but 1% will build up the light faster. The photon's energy of E2 to E1 bouncing back and forth between the mirrors is going to stimulate that avalanche of the new photons. And so that's what's doing this effect here, is you're continuously boosting ones up, right? Using that pump. So you're boosting stuff up into this state. It's falling down then to here. And then when you pass the light that came off from the previous one, it's going to cause a stimulated emission. Is that making sense? Okay. A little bit like juggling if you think about it. So you're passing it over, and then you can throw. Okay, and so what's going to happen here is you're going to space these two mirrors here on a multiple of that wavelength. So that's one of the key factors here, is that this is going to be a multiple of that wavelength right here for the optical cavity. And it being an exact multiple of the wavelength means it's going to coherently build up energy intensity, isn't it? By refracting it back and forth. Okay. That small fraction of your light that's passed through the partially transparent mirror, this is actually your output that you're seeing of the laser. So most lasers that you're seeing, you can pulse at much higher energy outputs than what you're seeing. Okay? It would deplete the system, though, if you do that, because you wouldn't have the light coming back through, and then you'd have to build it back up, wouldn't you? Okay? But most lasers that you're seeing, it's only a small fraction of the actual power inside that system. Like a 1, 2, 3% maybe, but usually more like 1%. So the laser diode, this is going to be your population version of your charge carriers. In a semiconductor, it's going to be achieved by a high electric field across a p-n junction. Electrons promoted to the conduction band are going to recombine with holes left in your valence band. These are where going to emit light. The emission wavelength is actually going to be determined by your band gap of your semiconductor material. And so the development of semiconductors greatly helped out lasers, or maybe vice versa too. Honestly, it went both ways. But this right here is your laser active semiconductors here. And this is your typical emission wavelengths that you can do with those semiconductors. And so these are the band gaps that you would see for those semiconductors. You can modify the band gaps to some degree. And those band gaps are going to be what are actually being used for this energy difference. And that's how you can select those. And so, for example, you'll see quite a few of these are just like, we're just taking different dopants, different molecules, and inserting them to modify that band gap. Can you see that? Okay, so let's talk about LEDs, light emitting diodes. These again are going to be based on the same recombination of holes and electrons in a p-n junction as your diode lasers are. They just don't have an optical cavity. And so whatever power you put in, you get the same amount of power, well, a slightly smaller amount of power coming back out, right? Minus the waste energy. And so LED photometers, this is going to be limited to a dedicated wavelength per diode. You can combine diodes to get more coverage, but it's going to have a pretty narrow band around each diode. Not as narrow as a typical laser, though, but very, very similar to a laser. Okay. They'll consume low amounts of power. They're very good for portable devices, as you already know, because probably your phones are an OLED or an LED screen, right? And so you're already very familiar with LEDs to some degree. The pulse oximeter is actually a device that you clip to a transparent part of your, like a fingertip or an earlobe. It actually emits 660 nanometer red light. It's near the infrared 940 nanometer emitting diodes on one arm of the clip and 2 photodetectors on the other. In the presence of oxygen, hemoglobin binds O2. This forms oxyhemoglobin. That's the reaction for that in equilibrium. Oxyhemoglobin and deoxyhemoglobin absorb differently, 660 versus 940 respectively. This enables determination of their concentrations and thus your blood oxygenation levels, right? And you've all probably seen that to some degree, where it's like 940 or 94% or 96%, and you probably have like a smart device that does that for you. Yeah. And that's how that works. Monochrometers. So the monochrometer, this is going to disperse light into its component wavelengths and selects a narrow band of wavelengths to pass on the sample or detector. Do you guys have any questions so far? Is there anything you're particularly getting stuck with? Because I do need to kind of, I'm going slow through this, aren't I? Okay, so there's a variety of ways you can do a monochrometer. Diffract gratings are one of the more common ways, and one of the more price advantaged ways of doing that. This can be reflective or transmissive optical component. Do you guys know the difference between refractive or transmissive? You got it. Bingo. Diffraction is going to be bending of light by a grating. And so this right here is diffraction, right? We're diffracting it so we get the different components of light. Notice that your incident beam going straight forward typically gives you back your same mixture of wavelengths. Okay. And so you can actually get, that's like that silver. If you ever rotate a CD, you can see like it where it gets really bright and silver. Refraction is going to be the binding of light by a lens of prism. So this is a transmissive grating. This is actually how the gratings work. So when you have the incident light here, they're going to have a distance here that's between the two. This is the grating equation that goes along with this. And so you have n times the wavelength, so a multiple of wavelength. And this value is going to be equal to the distance right here of the gratings. See, those are those cutouts, the grating. Okay. And then this is going to be your angle right here. That is going to be the diffraction angle. Okay. And so what you'll see is that the angles where you have an integer of wavelength is going to be equal to the increase of the path length. Adjacent light rays are said to be in phase and reinforce one another. If they're out of phase, they're going to cancel one another, right? Or destructively interfere with one another. Okay. Have you guys done any of this in physical chemistry yet for quantum? Okay. Okay. Yeah, I was curious because this is one of the sections in quantum you'll hit on. Yeah. Okay. Do you guys see how to use this equation here, by the way? Okay. And this is why, for example, when you move the grating of like a CD, it changes the light that's reflecting off to you, right? Is you're changing this incident. Is that making sense? And you're selecting for different wavelengths because you're selecting for different multiples of the wavelength. If you were to keep going through a motion, by the way, would you see the color once or would you see it multiple times? So let's say we took this grating, we had a light source coming in at a perpendicular, and we just slowly move it, fractions of a degree each time. Yeah, you'd see each color, and then you'd see another round of each color, right? And then another round of each color. And you do that, several times, depending on the multiples of your wavelength, depending on your grating. Okay. So this right here is the waves in phase. That gives you constructive interference, right? And so you get an amplification of that wave. Okay. This is the waves that are partially out of phase, and so you see destructive interference, but not complete destruction, right? And so you get a partial result. Okay. And this right here gives the waves completely out of phase, and so you get destructive interference there, and that completely cancels that out. Okay. This is the Czerny-Turner reflection grating monochromator, and you may recognize this from the previous examples that was given. This is probably one of the most widely used monochromator. There are a few other monochromators that can be done, but this one is, I'd probably say 90% of instruments out there. Okay? If you have a monochromator in it, it's probably some version of this. There are other ones, though, that are not grating dependent, that are FT, Fourier transform. Now, polychromatic light, this is many wavelength light, enters through the entrance slit. We refract it off this collimating mirror. Everybody see how it's bent? It's concentrating it into a beam. That distance depends on here. And what it's doing is it's taking what comes through the slit. See, the slit has an angle to it, and it's spreading out. It's adjusting that back so it is a parallel beam. Okay? And so that's collimating. Everybody okay with that? I.e. making the light into a column? Okay. Same as that laser we were talking about? Okay. And so that's then going to hit the refraction grating. This will be on a rotating platform. That platform needs to be able to adjust very, very small increments. We've actually run out of time. This is then going to go on to a focusing mirror that's going to focus it down into a beam to go through the exit slit. you will notice this is going to give some degree of angle back to it because you want to focus that beam down. It will then re-expand so that it hits the photo detector at the right angle. Okay. You can sometimes put an aperture here to eliminate some of this extra light if you have to. We'll stop here, I guess. And man, I am taking a long time on this material. Sorry. Is it at least useful? Okay. Yeah. As long as it's useful, that's good. Mm-hmm.